let's look at how our breathing alters during exercise. Now at rest, we have a normal tidal volume. It just goes in and out, quite relaxed. We don't think about it. And it's just something you do. You can do it in your sleep. That's how good you are at it. So it needs to be altered though if we provide a different demand on the body. Now, a main demand that we always provide on the body is exercise. And this can happen by chemical signaling or by neural signaling. So you are in control of your breathing, but as you begin to warm up in sport or something like that, then your breathing rate will start to automatically change. And those are two ways, chemical or neural signaling, that can start to trigger a change in your breathing rate. So just back to this. At rest, you're looking at about 14 breaths a minute at rest. That can be a lot lower. There are people reported to have 6 breaths per minute, and that comes down to, again, size, shape, training history, and training type as well, leaning more towards the endurance athletes. And then looking at you during exercise, it will double somewhat to get to nearly 32 breaths a minute plus, depending on the type of exercise you're doing. So the chemical signaling. So if we were to take a cyclist and we go riding and we go up a hill, we can go from a resting breathing rate to a type of breathing rate that suits the difficulty of the exercise. So if it's a very hilly route that we're going to take, then our breathing rate will increase as we go up the hill and then drop down to more of a normal resting breathing rate as we go down the hill. So the concentration levels of O2 and CO2 change, and we need to keep that balanced as much as we can. Now, too much carbon dioxide will trigger chemoreceptors. So chemoreceptors pick up chemical changes, and CO2 provides a chemical change. All right, so it's picking up a difference in acidity. So too much CO2 provides too much acidity within the blood vessels. That message gets sent from the chemoreceptors to the brain, an area called the medulla oblongata, and that makes some decisions and makes some changes to help us breathe differently. So we can breathe deeper and faster to accommodate this new change of CO2. Now, the neural signaling, while we're cycling, this is more to do with the electrical wiring that we have inside the brain that's connected to the lungs. Now, this is responsible for sleep. So while we're asleep, we have absolutely no control over anything that we do. So this neural signaling breathes for you while you're asleep. So messages initiate them from the medulla, and they can make these changes to breathing rate in relation to the exercise intensity. So it's telling you to breathe in, breathe out, breathe in, breathe out. So the respiratory to the medulla at the same time receives signals from chemoreceptors to make the required adjustments. So this can be different based on how steep the hill is as well. So if the hill is very steep and long-ish, then you'll be working to the most highest capacity you can. You'll go into your total, you'll use up all your inspiratory reserve volume and use up all your expiratory reserve volume. And there's only really so long that you can do that because the acidity within the blood just gets too much. And some people then have to get off the bike and then walk the rest of the way. So, quick snapshot at it. Muscle cell respiration will increase, which means it's going to use oxygen a lot faster, which means it's going to produce carbon dioxide a lot faster. And this is when the brain signaling starts to kick in, because it's going to pick up the change of this carbon dioxide. So it's not really noticing anything to do with oxygen. It's really picking up the problems with an increase in CO2. because it recognizes the acidity. The breathing rate will then change. It will go deeper and faster, so we can breathe in more and we can breathe out more, and that then becomes your new tidal volume for breathing. The brain signals the heart. So because your breathing rate is now helping to get rid of the carbon dioxide, all right, and the acidity inside the blood, we also need to bring in more oxygen, which it's doing by breathing in deeper. So it's breathing out deeper to get rid of the CO2. It's breathing in deeper to bring in more oxygen. Now, that is good, but it isn't that good if the heart isn't pumping quicker. So we still need to move and shift that blood and gases around the body. So the heart and lungs have to work together. So if the breathing rate of the lungs is going to work faster and better to change the balance of gases, we need the heart to respond in order to move these gases around quicker. So we get signals sent to the heart, which will hit the SA node and the AV node in order to beat quicker and beat bigger as well.